This is a lesson on transformation of functions in a precalculus course. Transformations for me is a starting place where we relate what is happening on a graph to what we see in that equation. So as we think about an equation, a function, g of x, if we do transformations on different parts of this original function, we can transform that function in different ways. Remember, there's toolkit functions, the standard function. Some of them are just like a line or a parabola or a cubic function or an inverse function. We might have an inverse function. That's also a toolkit function. So we have basic toolkit functions where we do a basic operation on x, and what we can do is take those basic operations and do transformations on them. So this is, to me, more geometric transformations where, and you may have studied these before when you first learned the Cartesian coordinate or geometry, where we shift things around on a graph. We can invert them and we can make them bigger or smaller in different ways. So those are just basic transformations on our basic, what we call toolkit functions. All right. So 3 of them I'm going to highlight today. There's going to be a shift or translation where we just move something around. We relocate it on a graph. It'll look the same, but it's in a different place. And what we're going to do is add or subtract constants to the input. So our input is the f of x, so that's referring to this b value. Or we can do add constants to like the whole function. So that would be this outside thing. We can just move it like up or down by just adding a constant. Okay. There's reflections. If I had these parabolas, they point up. If I do a reflection, if I multiply by a negative sign, it'll point downward. So watching out for what that means in terms of symmetry around axes. We'll talk about that. And then scaling. If I just multiply my function by a number, what does it, how does it change the graph, right? We can have a compression or stretching, and we can have it horizontally or vertically. And that depends on this a value. And I'm going to talk a little bit more in detail. I have a point in this lecture to talk about that in more detail. So let's first start with something that is, to me, a little bit more of the basic transformations where we're just doing shifts on a graph. And I'm anchoring this information in your mind for you in thinking about the equation for a parabola. If you studied parabolas before, and I actually expect that you have, we know that the vertex, when we read this general parabola equation, a quadratic, right? We can read the vertex off of this equation. The vertex is at h, comma, k. And notice, very importantly, when we learn this material, there's a negative sign here and a positive sign there. Those are very important because that means I shift left or right. Right? So a negative sign is different, or I shift up or down. A negative sign will make the difference. So when you look at a problem like this, you may see a problem like this in your work. That's what they're referring to in h and k is the vertex of the parabola. HK. But when I teach this material, notice on the equation I had on the page before, I was highlighting B to be a shift in the input value as opposed to C being a shift on the output value. So that corresponds to our H and K that you're familiar with before. Okay. So let's anchor this a little bit more. If we shift the input variable, if we subtract or add on something to the input, when I input it into the function, I'm going to input that value to the left or the right. So instead of starting at 0, when I input, let's say I do a -1, if I shift it over to -1 here, I am shifting that over. When I plug the value into the equation, into that parabola and evaluate it, I'm starting 1 over, so I'm going to see that the values that correspond to 1 are actually going to line up on 0 because it's negative 1 over, right? Same thing for this one, negative 1 over. So we're going to get a parabola that's going to be centered at this new value, negative 1 for its vertex on the x-axis. Okay, so that's where the b is. And notice that when I plug this into the equation, then my new g of x will equal some constant a out front. So that's what we're going to call a, times x minus negative 1 squared. All right, I didn't shift it up or down with any c over here. So our equation is just going to be x plus 1 squared, and that means that I've shifted it to the left. Left if positive, right if negative, and it has to do with that negative sign in there. Much of the other transformations that we cover is going to be much more straightforward than that. This seems to me like to be the only trick, is left is positive and right is negative, which is different than the c on the bottom. You just add a constant. If it's positive, you move it up. Positive up, negative down. But with horizontal, it's kind of the opposite of what you might think intuitively. So when you're doing these transformations, this is more of the simple one, you're going to notice in the equation any shifts in the input variable or shifts of the output variable with a plus a constant or a minus a constant when you look at that equation. What's important to me, and what maybe you kind of took for granted, you didn't notice as I was doing this, is I had the graph there right away. I'm going to remind you that where I started this lesson is that what we see in the equations is intimately related to what we see on that graph. So when you're doing transformations, it's important to me, and I think it's important to you to get into the habit to look at both those representations at the same time. Look at that equation and get the graph out. Start looking at what features on the graph, what points are where, and how that relates to what you see in that algebraic expression for your function. So let's look a little bit more deeply at this. I have just a parabola, same old parabola, so let's practice a little bit more with a parabola. We're going to do this more as we move through the different toolkit functions this quarter, but I wanted to just start with something that was familiar for you. So this is the original toolkit function. There's nothing being done to the C function. If I want to shift the input variable, I'm going to shift it right. I'm going to shift the input by, remember the negative sign in there, so this will be negative 2. So that means that I'm going to shift the whole graph to the left. Okay, describe and sketch the graph of each function. So right now I'm describing what's going on. I'm going to shift that input by negative 2, and that means that I'm shifting the whole graph to my left. Okay, which is different than the next one down. When I look at that, it's not, that constant isn't next to the x in the squared term. You see that? It's off to the side. And to me, this means that I'm going to shift the output by a positive 2, which means that I'm going to move it upward. Okay. This last one down here, I have two transformations going on for the relocation. And remember, this is the HK version. This is the HK version. So when I look at this, I'm going to note that there's a negative 2 here, which means that I'm shifting to the right by 2. And I have a plus 2 over here, which means I'm doing up by 2. And so that's what the graph, when I describe these graphs, that's what I expect to see on those graphs. I can already predict what I see on the graph by what I see in that expression. Of course, I have the graphs. And let me move this over here. We can identify each one of these different versions of the equation, right? Each one of these shifts. So the green one here is the original function. Notice its vertex starts at 0, 0. The next one down, red, I made this one red. This one is the red graph here. And we can see that it shifted to the left -2 from the original one. The next one down, we can see that we expect the original graph to be shifted up by 2, and we can see that's this blue graph here, right? That's the blue graph. I'm shifted up by 2. And this last one, we can verify that I'm going right 2 and up 2, right 2, up 2. So that is this graph here. All right, so we're just moving the original function. We didn't do anything to change the shape of it in any way. We just relocated it on a graph. We're going to do some changing the shape. Another way that I can change from the original function is a reflection, and I had mentioned that on that introductory slide. When we do reflections, we're going to take our original function and we're going to flip it over the x-axis or the y-axis. So a negative in the input as opposed to the negative in the output. Okay, so that's what you'll see. So a horizontal reflection is I negate the input, and then I'll mirror across the y-axis. So when I look at that, that's going to be this red graph on the red line on these axes. The original function is the blue. We can see it starts here on the x-axis in the negative, and it increases upward. If I flip it over that y-axis, I'm going to use that y-axis as a mirror and flip it over. So whatever point is in a positive x here, I'm going to negate it and have it be a negative x on the input, and that results in a different output, right? So that's a horizontal reflection, which now you're seeing, you have an intuition what a vertical reflection is going to be. I'm going to flip it over the x-axis, and whatever point is the positive x here, it's going to stay a positive x, but it was a positive y up in this quadrant, it'll be a negative y down here. So you can see how we're negating the output rather than negating the input. This negates the input, this negates the output. That shows up different in that equation. When I look at the equation, it will come out in this a value, okay? In that a value, it'll have a negative sign or not, okay? If the negative is out front of some function of x, that'll be the negation of the output. That'll be a vertical reflection, as opposed to if there's a negative in here, popped in here, a negative right in there, I'm negating the input, and so that'll flip it over the y-axis and be a horizontal reflection, okay? So when I think about reflections, and I had mentioned this before when we talked about symmetry and even odd functions, reflections have to do with the negative sign, right? And when we looked at even and odd functions, that had something to do with the negative sign. Remember, even and odd functions, by definition, there's a rule for if something is even. When I plug in negative x into the original function, I get the original function back. I get a plus of that value. If I put in negative x into the function and evaluate it and get negative the function back, right? You see negative the function back. That's an odd function. Okay, so when I do operations, when I transform my functions, I may transform something from an even and odd function, and being able to tell whether something is an even and odd function deals with reflections about that axis. All right, so when I look at this toolkit function I mentioned before, f of x is x cubed. That's the graph there. If I take the negative of the input and input it in, I'm going to get a reflection over the y-axis. And so again, I'm mirroring. I'm taking the function and visualizing it on that graph and flipping it from left to right. And that's what happens with this function when I put in negative x, right? When I go negative x cubed, I get a negative x. So it flips. And I don't really see anything on this last graph that I want to talk about. I do want to move forward to neither function. So we reviewed what even is, we've reviewed what odd is, and I'm going to remind you that a function can be neither even nor odd. Even and odd seems like a binary and there should be just two options, but there's actually that third. It could be neither of those. It does not exhibit either rule for the input of x. Of negative x. When I input negative x and I get a positive function back, it's even. If I input negative x and I get the negative of the original function back, that's odd, right? So it does not exhibit either symmetry. Sorry about that. So let's look at this parabola. The original toolkit parabola here is a parabola, right? It's x squared. There's no shifts or transformations or reflections or anything. If I wanted to look at a similar function, or let me do this first. No. If I wanted to look at a similar function that may seem like it's even, but it's not even, is if I take this function and I just shift it over. This graph, I shifted it over to the left one. So this function is going to be x plus 1 squared. Remember that it's minus negative 1, so you get a plus 1 squared in there, right? So what you may think is, Professor Rose, you know what? That looks like it's symmetric. Like there's some nice symmetry. It's a nice shape. It's not wavy on one side and different on another, right? Like it's the same shape on both sides. But what I want to remind you is that we're flipping it over the y-axis. That is our axis of symmetry that we're evaluating on. And I have this other picture over here because I want to see the visual that comes from doing this. When I look at this picture and I want to rotate it, I can flip it horizontally, right? When I flip it horizontally, you can see that the original function and the flipped version are not the same thing. When I flip it over that y-axis, when I flip it horizontally, I don't get the same function back. That happens on this red function. If I take that graph and flip it over the y-axis, I get the same thing, right? But not on this function. So for me, and why I keep telling you, look at the graph, look at the graph, look at the graph, it's going to show me things that I won't be able to see in that algebraic expression. Makes it very apparent. If they give you an equation and they ask whether a function's even, odd, or neither, graph it. You may need to prove in the equation by plugging in negative x and proving whether it follows one of these rules. But if you just flip that function, if you draw it and then flip it and like that, right? Draw it and flip it and see what it looks like. And if it's the same function, it's even. That's it. You can test it and prove it with your algebra, but you're going to verify it on that graph, and that's the quickest answer. So this is a neither function. The parent is definitely an even function, but this is a neither. There's no symmetry. I did want to do this real quick while I was here and playing with some pictures. When I look at this graph here, if I do a reflection over the x-axis, it would make it point downward. Okay, so that's a vertical reflection as opposed to a horizontal reflection. You can see the horizontal reflection. The numbers flip. Do you see them on the y-axis? That's why you can't tell. That's why it's an even function. You can't tell whether I'm flipping it horizontally or if it's the original function, other than the numbers turn backwards. But a reflection over the other axis is definitely, you can see that there's a difference there. Okay, so check out your graphs. Definitely always check out your graphs. I have an example here for us. I really like this example. What we have is a function here. I'm just looking at it. I have not read the instructions yet. What I'm going to notice is that there's two terms here. There's this first term and there's this second term. This first term here, I recognize it, the toolkit function of an inverse. We'll study those a little bit more later in rational functions, but for right now, that's just like the basic one, right? 1 over x. This other thing is a line with a slope of 3. I recognize that as well. I'm going to notice also that I know back in my head a line is an odd function, and also an even is an odd function when you look at their graphs. You can check it out to prove me. It says use the definition of even and odd functions to determine if the above function is even, odd, or neither. It could be a neither function, right? It could be a neither function. So let's look at this. So I want to take f of negative x, right? That's going to be our test. If something is even and odd and I want to do this algebraically, I'm going to plug in negative x into the function. So when I do this, I get 1 over negative x plus 3 times negative x. So I'm going to simplify this. I'm going to get negative 1 over x minus 3x. And I'm actually going to do this to simplify it a little bit more. 1 over x. I'm going to pull that negative out of both of those terms. And what I'm going to note when I do that is I have the negative, and then do you all recognize this? This is negative f of x. So when I plug in f of negative x, what I get out is the negative of the original function. And that is going to tell me that it is an odd function. That is the definition of odd, is when I plug in negative x, I get negative f of x out. So good, odd. Graph the function to identify and describe the features of the graph that confirm your answer. What are we going to see on this graph that makes us aware for sure that it is an odd function? These two answers should correspond to one another. So as you know, I have a copy of this graph. I already did this and looked it up. There's our function here. All right, kind of interesting. There's an asymptote. I'm not surprised there's an asymptote in here because I have the 1 over x. Remember, x cannot equal 0 down there. So we're going to have that asymptote on the y-axis. All right. We also have another asymptote, it looks like, through here. There's another asymptote. I'm going to leave that for another lesson to find that asymptote. But when I look at it, when I'm looking at this function, I know it's not even. If it was even, there'd be something going on over on this side that would look like that, and that's not going on. So then I ask myself, well, maybe is it odd? And so if it's odd, I'm going to flip it over this way, and then flip it over that way, and that tells me that it's an odd function. I can see that on my graph. This is an odd function. Okay, so just to review reflections and symmetry, even, odds, and neithers. The last transformation I'm going to cover with you is scaling. Okay, and I mentioned this a little bit before with our parabola. There's that scaling factor out front. Remember, parabolas have an ax minus h squared plus k, right? So I'm thinking about this a value, that scaling factor. So when a actually, this is a little confusing. I might have said before that, you know, there's something confusing, but a can be confusing. For me generally, and I see this, I did the convention in the textbook. That's what you see here is the convention in the textbook. There's an a here. But there's two ways that a can cause a transformation in scaling, and so that is a little confusing for me. That's why I made these little details down here. We could have a, the scaling factor, we could scale the input, and that's not surprising, right? We've done that a couple of times already. Am I moving it left or right, or am I moving it up and down? And that constant goes in different places. Am I reflecting this way, or am I reflecting that way? That goes in different places in our equation. And when I see a different scaling factor out in front of the input as opposed to in front of the output, do you see where that a is in two different places here? Okay, that results in two different functions, two different transformations on that function in a scaling manner, right? And you see that on these graphs. If I put the scaling factor inside with the input, right, I'm going to get a horizontal stretch or compression. It's going to make it go like this. Okay. If I put it outside and I multiply the output by the scaling factor, that's going to make it taller or shorter. we call that a vertical stretch or a vertical compression. So I think the general form here is misleading because there's only one A and you don't see it in front of that X. But for me, and it talks further about it, is the difference between horizontal scaling and vertical scaling. Okay, so I've outlined these. And you can see it in here. If I have a fraction, it's going to make the function not increase as fast as the input. That's how I think about it. So I'm going to get a stretch on it. You think if you put a large number in there, it'll make it larger. It's actually the opposite. If you put a large number in the function, it's going to make it taller, quicker. It's going to compress it horizontally. Scaling, I think vertical scaling is pretty intuitive. If I multiply it by 5, then it's going to be 5 times taller. Okay, so when I look at transformations, I have these examples, and I did this before with you with the relocating. It's a very similar task, and I have the graph here already. Because we're just talking about it. The original function, again, is a parabola. I have the parabola here. And it is the green function, the parabola. The green one here is the original parabola. And I've changed everything by a factor of 2. Okay, so how does a factor of 2 affect? Well, if I put factor of 2 in with the input variable, I'm sort of like magnifying, I'm exaggerating that multiplication by doing a power on it. I actually get a 4x squared, right? So it's going to rise, it's going to move 4 times faster than the original function. And you can see that in here with the red line in here, the green to the red line, it's 4 times larger. As opposed to the blue line, which is twice the output of the original function, which is just this blue line. You can see that it's just a 2x squared. So for me, I'm going to highlight right here. You may see where they have a times f of x, right? In one situation, I have a 4, which originally looked like a horizontal compression. But if I play out that algebra, it can look like a vertical stretch. It's stretching vertically upward. It's growing larger. So when I think about these transformations with these constants, there may be a couple of equations that satisfy, and it may look like it's a horizontal stretch or a vertical stretch. In different ways, a vertical compression and or horizontal compression and a vertical stretch, vice versa. And we see that down in the bottom too, right? If I do 2 times 4x squared, I'm going to get an 8x squared. So I'm getting the same graph, and we're seeing that what looks like a horizontal compression can be represented as a vertical stretch. It can get confusing, and to me, that's why in that general equation, there's just a scaling factor out front. There could be 2 different scaling factors overall, and it depends on the function that you're looking at. I wanted to finish up here with something that, of course, you probably knew was coming, was transforming transformations. We're not going to do all these just to individually. You're going to have to look at a graph and do multiple ones at once. So identify or perform a sequence of transformations. We can have shifts, reflections, and scalings. All right. And looking at the graph and being able to identify, was there a shift? Was there a reflection? Was there a scaling? Okay. So I'm going to go back to this graph that we looked at a little bit earlier on the introductory slide. I don't know if you remember that's what it is. This original function f of x is the toolkit function x squared. The base function f of x is given in red. Write the equation for g of x in violet as a transformation of f of x. So here's g of x in violet. And it's our good old trusty parabola. So if I want to write g of x, I know that is going to be some constant, some scaling constant out front a, times x minus b squared plus c. And you could write an h and a k in place of b and c, but I'm sticking with the convention in the equation I introduced, right? Our original function was x squared, so I'm going to shift the input by b and the output by c. We also need to deal with this a factor. I can do b and c pretty quick. I just look at the vertex here, -3, -5. So I know that g of x has to be x minus -3, so I get a plus 3 squared in there, and then a 5 downward on the output. So I know that where those go in the equation looking at this graph. What students struggle with, and I like to put this question on exams because I know students struggle with this. They can get the H and the K, but they don't know how to do the A. We're going to do the same sort of trick that we might do if we know like the slope of a line but not the intercept, is we're going to plug in a point. So we're going to notice that there's some points on here. I'm going to go to the point, let's go point -2, 0. I like using smaller numbers. So wherever I see x in here, I'm going to put -2, and wherever I see g of x, this is our output variable, I'm going to put 0. So 0 equals a -2 plus 3 squared minus 5. Okay, you see when I plug that point in there, the only unknown left in that equation is that scaling factor a, and I'm going to use algebra to solve for it. What I see students do is they kind of play around on the graph. They'll pick a point and it's like, oh, it should be here, but it's here, so that means it had to be whatever scaling factor. I want to see algebra. I want you to be able to do this and solve it and prove it with algebra. So I'm just going to solve this equation for a. -2 plus 3 is 1 squared, so I get 0 equals 1a minus 5, so I get a equals 5. Is pretty easy on that problem. We're going to come across more problems when we get to more complicated functions later where that a value might require a little bit more algebra, but that's how you do it. You just plug in a point and find your unknown. So we may call this boundary conditions when you get further in science. So g of x will look like 5 times x plus 3 squared minus 5. That's the equation, right? The equation for g of x with all of the known values. So that's how you do that problem.